Alright, we're going to try 7.1, exponential functions and their graphs, and talk a little bit about that. We'll also talk about not only graphing them, but solving elementary exponential equations and inputting exponents and graphing exponential functions. Alright, so the next thing we've got to do is talk about what an exponential function is. An exponential function has a real number base, and the exponent is your variable. So in other words, this could be an example of an exponential function. Could be f of x or y is equal to 2 to the x power. It could be 1/3 to the x power. It could be any number, but the variable is in the exponent. Instead of having x squared or x is my y equals. So that's what makes an exponential function a little different. When we look at graphing it, we see that it has kind of a unique graph. Now this is a lot of words that tells you when it's decreasing, it's a decreasing function, which means it starts high and goes down and levels off. When a is a fraction between 0 and 1, or a decimal between 0 and 1, it's not negative. It's positive, but it's a small number. And it's an increasing function, which means it starts low and goes up to infinity as your x's get bigger. And in an a, your base, it has to be bigger than 1 for that to happen. And there's exponential growth, which is your increasing function. A is a number greater than 1, and exponential decay, which is where x is, or the base, is a fraction. So in other words, decreasing function, if we were going to call it a decreasing function, is exponential decay. So I'm going to write that here. Decay. An example of exponential decay would be 1/2 to the x power, or 0.6 to the x power. Your base is less than 1. Okay? An increasing function would be exponential growth. Okay, like a population explosion or something like that. Exponential growth. And in that case, your base is bigger than 1, so it's like 2 to the x or 5 to the x, some number that's larger than 1. Could be 1.5 to the x, as long as it's bigger than 1. Now, in either exponential growth or exponential decay, this point, 0, 1, will be on your graph. So that's always one point you can pick when you're doing an exponential function for growth or decay. That point is always on your graph. Alright, so let's move on to the next slide. So here's some of the following graphs of exponential functions. And what we're going to do, one easy thing to do would be to make a table for these and then to sketch the graph. Now this is probably on the next page, but I'm going to go ahead and do it by hand just so you see. We have x, and we pick those, and we have 3 to the x, which is our y value, because y is equal to 3 to the x. So I'm going to pick some easy x's. Let's pick -2, -1, 0, 1, and 2. Now with exponents, you may or may not remember, if I have 3 to the -2 power, that's the same as 1/3 squared, or 1/9. Okay? If I have 3 to the -1 power, that negative power doesn't make it negative. It puts that number in the denominator. So it's 1/3 to the first, or 1/3. Anything to the 0 power is 1. And that's why the point 0, 1 is always on the graph. Then we have 3 to the first, so that'll be 3. And 3 squared, which will be 9. Okay? Now, as you graph that, and I think it's going to be on the next page, but I'll draw a quick graph of it. I'm going to have to erase it to do the next one. Well, maybe not. Okay, so I've got -1, -2, 0, 1, and 2. So this should be an increasing function, which means it starts low and goes up to high, goes up to infinity. So we're at -2, we're at 1/9 So we're just barely over this x-axis. Right there, okay. At -1, we're at 1/3, not much taller. We have 0, 1 as a point on the graph. We said that was on all exponential functions. We have at 1, we're at 3, 1, 2, 3. Okay, at 2, we're way up at 9, so that'd be way up here somewhere. And so you can see the graph gets steep very quickly, and it levels off. It will never go below that x-axis unless it's a downward shift or transformation, because no matter how small, if I have 3 to the -27, is going to be 1 over 3 to the 27th power. So it's not going to make it negative. It's going to make it really, really small. So this graph never goes across that x-axis. It just gets closer and closer and closer and closer. Now let's look at the 1/2 to the x power. Again, I'm going to put this in. I'll put this in a different color just so that it you can see them. So this is, we'll make our table, our t-chart for our graph. We have x, and then we have 1/2 to the x power, and we're going to pick -2, -1, 0, 1, and 2. Alright, so I'm going to go off to the side just to do this work so you can see it. The first thing is going to be 1/2 to the -2 power, which is 1 over 1/2 squared. Okay? Now let's think about that. Remember that -2 puts it in the denominator, and then the exponent changes to positive. So that's going to be 1 over 1/4. Now when you divide by a fraction, if you remember way back in elementary school, you multiply, that's 1 times 4 over 1. You invert the fraction and multiply. So 1/2 to the -2 power is actually a pretty good, is a big number, and it's 4. Okay? It doesn't, this goes the other way with the negative, the fraction with a negative power gets bigger. A whole number with a negative power gets smaller. Alright, so let me erase this and let's do the 1 over 1/2 to the -1 power, and you can probably know where that one's going to go, but let's go ahead and do it anyway. We have 1/2 to the -1 power is the same as 1 over 1/2 to the first power. That's the same as 1 times 2 over 1. Don't really need that x there. 1 times 2 over 1, which is 2. Okay? So, for when x is -1, y is 2. Okay? Now, anything to the 0 power, again, 1/2 to the 0 power, it doesn't matter. 1/2 to the 0 power is 1. Anything to the 0 power is 1. 1/2 to the first power is going to be 1/2. 1/2 to the fourth power, 1/2 times, 1/2 to the second power, 1/2 times 1/2 will be 1/4. And so remember, it said when my base was a fraction, it was a decreasing function. So let's graph it and look at it, and it sure is. Okay, I'm going to have 1, 2, 1, 2, 1, 2, 3, 1, 2, 3. Okay, when x is -2, I'm up here at 4. Okay. When x is -1, I'm at 2. Then I have the point 0, 1, which is on all of them. Then at +1, you're at 1/2. And at +2, you're at 1/4. And so again, it's going to go from really high, it's decreasing down to the x-axis, and it just gets closer and closer and closer to that x-axis, but it never crosses it. And so exponential decay, this is decay right here, starts out big and gets smaller. And exponential growth is this graph that starts out very low and gets bigger. So that's the difference in exponential growth and decay. And you know by the bases. Again, if the base is bigger than 1 here, it's growth. If it's between 0 and 1, like this second graph, the 1/2, it's decay. Alright, so that's enough about that part of the graphing. I think they're going to show us the graphs. I plotted 5 points. They plugged in a -1, 0, and a 1 and made a curve. And you can see they got the same curves that we did. Now I want you to notice on this, though, I want to make a comment. Our base here was 3. So if I have a base to some power, okay? And in this case, there's 3 points that will always be on the graph. And one is 0, 1. We've already said that's going to be on the graph. 1, the other point is going to be 1, and the base is going to be your y value. And the other one will be -1 and 1 over the base, okay? So those 3 points are always on your graph. In this case, our base was 3. So I had 3 to the x for this graph. And so you can see I have 1, 3 as a point here. I have 0, 1. And I have -1 and 1 over the base, which is 1/3. Here, my base was 1/2. And so I have -1 and 1 over 1/2 is 2. So that's the same. Well, the point I got here, I have 0, 1, and I have 1 and the base itself, which is 1/2. So you always have 1 in the base, 0, 1 is a point, and -1 and 1 over the base. And those are 3 points you can plot for every exponential function without having to calculate anything. You just know their points on the graph. All right, sketch the graphs of each of the following. 1/2 to the x plus 3, -3x plus 1, 2 to the -x. So I want to talk about this a minute before we go any farther. Remember what our transformations were. So I'm going to kind of summarize. If it's grouped in with x, okay, grouped with the x, we had a horizontal shift. It was a horizontal shift. Okay. If it's a negative in front, okay, it reflects over x. Okay. If it's a plus or a minus at the end after the function, okay, that's a vertical shift. So it's going to be up or down. Up or minus would be down. Okay, hopefully you're remembering that. Now if you have a negative in with your x, negative with the x, okay, that's a reflection over the y-axis. So let's just look at these and make some predictions. Reflection, put an L in there, over the y. Okay, so let's look. Here, I've got this meets, it's grouped with the x, and it's a plus. So that should mean that my basic function is shifted left 3 units. Okay, and my basic function is a decay function, so it's going to look like this. And this point at 0, 1 that we know we have, okay, this point at 0, 1 is going to be left 3 units. And we'll check that and see if it happens. Now let's look at this, the second one. This one is a reflection over x. And this one here means it's going to go up 1. Alright, so let's think about our original function. This is a growth function. So the original function comes in looking like this, right? If it reflects over x, it's going to now look like this. Okay? And from this point here, it's going to shift up 1, so it's going to shift up this way 1 space. And we'll look at the graphs in a minute. Now this 2 to the negative x, I believe this is going to be a y-axis reflection. So what is that going to look like? It's a growth function. So it would normally look like this, but a y-axis reflection is going to flip it around the y-axis. And so instead of that, I believe it's going to look like a decay function because of that negative x. Okay. So let's take these notes away and see if we were right in our predictions. Okay, so as we go to the next page, we have A. So we've got 1/2 to the x power, and it's shifted left, so you can see the purple graph is the left shift. The original graph is the green line. And we did predict that left shift. So now let's look at the next one, B. We started with 3 to the x, which is the green line. It's a growth function. Okay. We reflected it over x, and then we brought it up 1. So the reflection line, if I was going to do the reflection line, it would be in here, right here. Excuse me, right there. And there, and here. So the reflection line would be this, look like this orange line, but then when it shifts up 1, it's where the purple line would be. So you can see the reflection, and then the upward shift. Okay. Now for C. Okay, for C. We started out again with our typical growth function, 2 to the x, but since it's up there, the negative is up in the negative, it's a reflection over y. Or you can also think that that makes it 1/2 to the x power, which of course then is the decay function, because it's 2 to the negative 1 times x, and 2 to the negative 1 is 1/2. So there's a couple ways to look at that. You can look at it as the reflection, which it is, over y, or change it to that fraction for the base. Either way, you come up with this. The purple curve is the curve after the transformation. So, solving elementary exponential functions. Isolate the part that has the exponent on it. Isolate the variable. So you get that exponent to one side of the equation and anything else to the other side. Find a base that you can find a common base. So find a common base and rewrite both with that base. Then you equate the powers. If the bases are equal, the powers have to be equal. And you can then solve a pretty simple equation. So we'll work some examples so that you can see how that works. So we have 25 to the x equals negative 125. So let's work through that one first. Okay. And we'll work in green. I feel I'm in a green mood. Okay. So we're going to say 25 to the x. And we're going to add 125 across to the other side. Now, we need a common base. Well, 25 is 5 squared. So that's 5 squared to the x power. And 125 is 25 times 5, so it's 5 cubed. Now, if you remember from exponents, when you have parentheses raised to a power, that becomes 5 to the 2x equals 5 cubed. And so from there, it's pretty simple to solve. Okay, and it's just, since our bases are the same, we just set our exponents equal. 2x equals 3. And so x will be 3 halves. And that's our answer. Okay. Now let's work the middle one. We have 8 to the y minus 1 equals 1/2. Don't have to move anything over. My variable with the exponent is there. What common base could we get? Well, we're going to say a common base of 2. 2 times 2 is 4, times 2 again is 8. So 8 to the y minus 1 is the same as 2 cubed to the y minus 1. Okay? Now, 1/2, remember, and putting that 2 in the denominator means it has a negative exponent. That's the same as 2 to the negative 1 power. That's the same as 1/2. Okay? Now, when we have this parentheses to a power, that is this 2 is to the third, to the y minus 1 is the same as 2 to the 3 times y minus 1 equals 2 to the negative 1. So now I have a common base. So I can say 3 to the y minus 1 equals negative 1. If the bases are equal, the exponent, you set the exponents equal to one another and solve. So then I'll distribute the 3. 3y minus 3 equals negative 1. You add your 3 across. 3y is equal to negative 1 plus 2 plus 3, so that's going to be 2. And y will be 2 divided by 3, or 2/3. Will be my final answer for that one. That's B. Alright, so let's look at C. C is a little bit tricky. I'll grant you that it is. So let's look at C. So we're going to start out with 2/3 to the L of that to the x power. So I have 9/4. Well, 9 is 3 squared and 4 is 2 squared. So that's 9/4. And then we can get to a base of 2 and 3, but they're on opposite sides. So what do? Maybe we need to do a reciprocal. So if I make this I can write the 2/3 as 2 to the negative x, and that becomes 3 over 2x. So let's move on. I'm going to move on to their slide and make sure that I would do it the same way they would do it on this one, because it is a little bit tricky. So let's go back, and I'm going to erase these, and we'll move on and show their solutions. So here's the solution for A, and they're going to get the same thing we did. You can see that as we walked it through, we get the same thing they did, 3/2. Okay, then B, again, you get a common base, distribute that 3 or multiply it across, and then set the exponents equal, solve it, and you get 2/3. Now let's look at this one. Again, the base is not obvious. So we've got 2/3 to the x is equal to 3/2 to the squared, or 3 squared over 2 squared, either way. So now we need to put one of them to the negative power. So to make them they're going to flip over. I think I would have flipped over the one on the left. They're going to flip over the one on the right. So by making it, instead of squared and negative 2, that you can write that as 2/3 to the negative 2 power, because when we then made it, that's the same as 3/2 squared. We haven't really done anything different. We've just written it differently. It defines the same number. Now we have the two bases equal, and so x is equal to negative 2. And that would be our answer on that one. And that one's very difficult. It's much harder. So this is a caution. 3 times negative 3 is positive 9. We know that when we do it in our head. We know that negative times negative is a positive. But sometimes when we put another in the calculator, if you type it in like this, it will give you a negative number because you're not telling it to, what that calculator is saying is that you're saying to square just the 3. It's negative and then 3 squared. And so what you'll get is a negative 9. And that's wrong. So don't let your calculator give you a negative number in these cases. If you're going to square a negative number, be sure you put it in parentheses. Okay? Because that way it knows to this that you're saying negative 3 times negative 3. Otherwise it doesn't, and it will give you an incorrect answer. And I get frustrated, but it happens a lot because students will get a wrong answer and they believe their calculator rather than their brain. So don't do that. Be careful. That's the end of section 1.